Hi, my name is Walid Al-Ghami, and this is Lab 3 Physics 2211. As an intro, the purpose of this lab was to analyze the motion of a star orbiting a black hole, and using Newton's second law, infer the mass of the black hole, which is unknown. Right? And two is we also used the second law of motion to simulate a spaceship's trajectory in this interactive system, star and moon. The fundamental principles we use in this lab is the first law of motion, second law of motion, which becomes very important, especially in the first part, and position update formula, just to iterate the position of our ship and star later on. For the main results, for part 1, we essentially got an average mass of 9 times 10 to the power of 33 kilograms. And for part 2, I managed to get an 8-figure trajectory using these two x and y speeds. So why we use the fundamental principles? The second law states that if a force occurs, momentum will change. In a gravitational field where there's this big black hole and something orbiting it, there must be a force that changes the orbit or the momentum of some object around that, right? So in part 1, essentially what we're trying to do is for delta V equals F over M times delta T, we are trying to solve for, this is Fg, right? We're trying to solve for the mass of the black hole. So we can use this equation with the knowledge of how momentum changes to solve for the mass. Now for part 1, solving for the mass, we essentially have our initial conditions right here: gravitational constant, the mass of the star that is orbiting the black hole, and delta T. Okay, we identify our momentums. It's important to note we are given momentum, right? So the process here is we know what the momentum is, and therefore we know what the force is, and we equate that force to Fg, right? Because it's the only force there is gravitational force, which is Gmm over r squared. And we know G, we know the mass of the star, we know the distance, but we don't know the mass of the black hole, right? So essentially we go through all of this up to here. This is the most important line right here, the mass of the black hole. And this is the equation. This is simply just, if you plug in the second law of Newton, the second law of motion, if you plug Fg in, the formula for gravitational force, and you solve for the mass of the black hole, this is what you get. And so our simulation essentially just iterates through this and prints out each mass at each interval. And then you can average it out. For part 2, everything is given and shouldn't really be changed. So these are my initial conditions. Then the speed and velocity for the moon is already given. I used a 2-month window. Any more than that, my trajectory would just blow up, really. And so I played around with the speed in the x and y direction, and this worked for me. -2 times 10 to the 4, and 2.5 times 10 to the 4. So then you have this while loop where you update the, essentially you update the force, then you update the force essentially from the ship on the moon, the force of the moon on the ship, and then you update the velocity and the ship velocity for both the moon and the ship and their positions. Right? The main results, as I said before, we got this average mass basically by doing what we did back here in the previous slides. In part 2, we got this 8-figure thing or trajectory, since the moon is moving, but the star that you're orbiting does not. Now, what does it mean? What is the difference between Fnet and its components and the momentum? You can actually see it right here. Fnet is just the change in momentum. The momentum is a vector of magnitude of the momentum times the momentum's direction. So it's Fnet is really this central yellow-orange arrow, and it just tells you the change in momentum in its entirety. Fnet parallel, the thing that is parallel to an object's motion, tells you how the magnitude of momentum changes, the magnitude, the speed, right? And Fnet perpendicular, the thing that looks outwardly like this, tells you not how the magnitude changes, but how the direction changes. So Fnet perp or dp dt perp is what's keeping something in orbit, right? It's changing its direction inwardly. Now, what if you wanted to simulate for part 2 the black hole, star, planet, Earth, moon, ship, etc.? Well, you need to evaluate all of those forces and update all of those positions and velocities. That gets really complicated, right? Now, there are dominant forces. So the black hole is the most dominant, then the star, then the planet, then the Earth, then the moon, and ship. So you can neglect some of them depending on how they change the simulation to make it easier. Now, possible errors, we could have done some incorrect force calculations, especially for the mass of the black hole. If you didn't solve it correctly, you could get wrong answers. And time step issues for part 2. If you have a large enough time step, the velocities could be way different than what they should be if the time step was lower. To conclude, this lab explored gravitational interactions and showed us how we can estimate a black hole's mass if we know how, if we can observe motion of orbits, right? And it just demonstrates how complex multi-body systems can be. Thank you very much.